Hi, I'm John Bucklew, and I'm one of the two members of Team PlayerOne, and I'm going to walk you through our solution for the Intel Challenge at the OSU Hackathon today. So, to start off, I want to cover some of the challenges we faced in trying to take on this goal. And the biggest challenge we faced was just getting the hardware to function. Starting with having to diagnose the whole power delivery solution, to the stepper driver boards overheating, to the software even being able to upload in a functional state. Eventually what we realized after a number of hours of troubleshooting was that in order to properly program this Arduino microcontroller board, you actually need an Arduino IDE 1.8, which is an old legacy version of the software. And that detail wasn't really noted anywhere that we could tell. So going forward, a suggestion for improvement that we'd like to implement is providing clear instruction sets for anybody else to replicate this hardware build. And with that, they should be able to do it relatively simply and quickly. With that being said, I'm going to pass it off to my teammate Prashant, and he's going to explain the user interface.
The photolithography stage controller. Hello, I'm Prashant, and this is the software backend that I've built, which can communicate with the hardware over here for the Intel Challenge. As you can see, for the USB microscope that we were given, I have made this live feed which can transmit through the React frontend that I've built, which is very UI friendly for any user to use and see how it works. And it communicates over a Python backend where endpoints are based on up, down, left, right movements based on the step sticks, circulation, revolutions, and in turn moves the X and Y axis. And the Python code helps in serializing this output into the Arduino directly to communicate like that. And as you can see, I've built a simple user interface where
show the features.
We can have the left, right, up and down. For example, if we have this move stage, you can see that the Y axis moves up, hence indicating it moves up for 1 millimeter. I have calculated it mathematically already here, in which one revolution is equal to 0.5 millimeters. And there's the steps inside each of the motors, which has 200 steps, which equals to 1 revolution.
Show the pattern. We got a minute left.
And then in coming up to the next interesting interaction that I've built here is this grid drawing, which basically mimics how lithography's silicon wafers are etched onto silicon wafers, where if you have a transistor drawing, you can have a number of points to draw up a pattern, and when you want to simulate the stage movement, you can see these micro adjustments happening to draw out and etch out this in perfect precision. And this precision goes down to a single step, which is in micrometers of precision inside, as you can see on the calibration sheet.
Thank you for considering our project.
PlayerOne.